Hello, my name is Philip Pearson, coming to you from Mountain View, California. Tonight I'm going to be building up a few of these circuit boards. It's a power-on self-test adapter for the Acorn computers from the 90s, the Archimedes and A series machines. Really why I'm making this video is to show that soldering using a paste stencil and a hot plate is not all that difficult, and it's possible to achieve some surprising things. This board doesn't have anything insanely complicated on it, but I've successfully soldered 0.8mm BGA chips quite happily. So, step one, we take our paste stencil. This is one, it's a stainless steel stencil I got from JLC. Fresh out of the box. Complete with all its plastic. So what we're going to do here is put the circuit board on the under the stencil. Align it through trial and error. Spread some solder paste on. Place all of our components. And then put it up. And everything will get soldered. And then fix all the inevitable problems. The trick is basically find the biggest pads, most familiar pads, align on those, try and find the same on the other side, align on those, look through from the top, hope you got it right, tape the thing down. So, here we go. Looks like I got that right. Okay. I do pretty much all of my work using this OptiVisor. It's a DA4, I believe, with a quasar lighting attachment, which is a little finicky at times, but works really well. So I use ChipQuick SMD291AX. It's tin and lead solder. I don't use any, it comes with quite a few attachments, I don't use any of them. I just squeeze it straight out from here. So squeeze out a reasonable amount of it. And then use a spatula. Is that coming out okay? Yeah. Use a spatula. I didn't clean it off after the last one of these that I did, so it's not spreading as well as it should. But you can always go back over your tracks if you're not doing an ultra fine pitch board. As long as you get, this is terrible, but as long as you get enough solder paste on, as long as you get some solder paste on all the tiny pads, and you get some solder paste on, well, enough solder paste on the big pads, then it's all gonna be okay. Alright, I need to clean that after this. Very carefully lift up your tape, and hopefully, let's see if this focuses. Yeah, you can see we have paste all over the place. it looks like it's possibly bridged some pins on the FPGA, that big one in the middle. In fact, we have tons and tons and tons of paste, probably way more than we want, but it usually works out fine. Now, is that centered? Good. Okay. Alright, so I usually print out the bill of materials and write notes on it. So, for example, up the top there, it's all my 100 nanofarad capacitors. There's 12 of them, so I make a note about that. Sometimes I tick them off. Today I've come prepared and actually stacked up. I have a stack of components that is already in order. I also have this printout of the silk screen with the circuit board with all of the 100 nanofarad capacitors marked out in purple there. I believe the way I designed this was to make a note on the silk screen for anything that wasn't kind of the default value. So for capacitors, that means anything that's not 100 nanofarads. That's basically the only default value I had. So, okay, so I have a whole reel of these. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 2, 3, 4, 5, 6, 7, 8, 10. Okay. So, there's lots of ways to do this. You can go from biggest to smallest. Sometimes it's good to put the most difficult component on the board, just in case you do such a bad job of it that you need to wipe the solder paste off entirely, start from scratch. I've found, I mean, this board, it doesn't really matter. No matter how badly I screw this up, it'll still be recoverable. So it's totally safe to do the easy ones first. Also, this is the first time I've done this in a while. So, starting with the easy ones. 1, 2, 3, 4, 5, 6, 7, 8. Now, there's the decoupling capacitors for the FPGA in the middle there. It's a little FPGA, and I'm not pushing it very hard. I think at max it's running at 48 megahertz, but why skimp on the decoupling? As you can see, it doesn't take long to place a whole lot of identical capacitors. Alright, that's our 100 nanos. Now 3 1 microfarad capacitors. Where are they? C1, 2, and 5. These are for the regulator. And the third one is for the Atmel microcontroller with its built-in regulator. Okay, now it's time for 4 LEDs. We want 2 yellows, a red and a green. Red, yellow. This was one of those fun things where I ordered a bunch of them from DigiKey, and they've shipped me like one package with 3 LEDs in it and one with another 17 or something. Okay, hopefully I can remember this. The yellow ones are L3 and L1, and there's that green arrow I think is the direction of the diode, and I don't remember which way around this is, but let's cross our fingers and hope that the arrow on the LED means the same thing as the arrow on the silk screen. Okay. Has that been out of frame the entire time? Hopefully not. There's one green LED. Green LED is the one that lights up when you have connected the target correctly. Powered it on. Now you'll see some of the time I have frightfully unsteady hands, but I can still get these things placed eventually. It turns out you don't actually need super steady hands to pull off some pretty fine pitch kind of placements, because you always have more than one chance. Solder paste is kind of sticky, but not so much. It'll grab the component and make a huge mess, unless you really mash it down. Red is the LED, which lights if you have connected up the target machine backwards and powered it on. Okay, what's next? Next are some chips, which I'm going to skip to start with. I'm going to make myself a jumper for, because I don't have any actual 0 ohm resistors, so I just fake it up by chopping the leg off a resistor, chopping it way too long, chopping the leg off a resistor, soldering the wire in there. There we go. Nice and stable. What's next? Next is actually a diode. This is the shock diode, which we use on the reset line to make sure we only pull the reset line low. Or in the case of everything being connected backwards, that we don't do anything really weird. Next is 100k resistor. Look at that, fresh pack of 100k resistors. I should maybe bring this a little closer to me so you can see me unpacking these. As you can see, this is my first time trying to record one of these. Hopefully it will still be informative. The plan here is to not cut anything, just let you see the whole tedious process of putting this together. See exactly what goes into it. It's for 10K resistors. Where are the 10Ks? 10Ks are 1, 9, 10, and 11. 1 is over by the microcontroller. 9, 10, and 11 are probably, I see 11. These are pull-ups or pull-downs for something. There's 10. And here is 9. Okay, now we need 4 1K resistors. This was before I realized that. Keeping them on the reel is miles better than cutting them, separating them off. I thought this would be easier, but in practice it just means you're always having to open up new little bags. Okay, where are these 1K resistors? 1K, I see one there, it's our 2. What have we got? 2, 7, 8, and 14. You'll notice that I'm not putting these components exactly, like lining them up exactly perfectly. It turns out that you can get away with that. They kind of align themselves fairly well during the reflow process. There's 14 down there. Okay, what have we got next? We need a single 2K2. Why a 2K2? Oh yes, that's right. This is something spec'd by Acorn. It's a pull up on D1. So it registers, it reads as 1 when there's nothing on the bus, which is the case when we are pulling up the ROM enable line. It's an ingenious little communication system. It works when pretty much everything else is broken. Here we go, 4 330 ohm resistors. What are these? 3, 13, 21, and 22. I believe these are all for the LEDs. Talking of LEDs, I have a little experiment on the circuit board. Everything up to version 2 used these single color LEDs. This one here, I've added a WS2812. The latest version of the WS2812 addressable LED is TTL compatible, so you can drive it from 3.3 volt logic, which is lovely. It means I can stick it on a board like this as an indicator without needing to worry about level conversion. Okay, R4 and R5. R5, oh there it is. And we've got some 4K7 resistors here. Not a value I usually use, but it's spec'd by Lattice as pull-ups for their LED, for their FPGA. And finally, 368 ohm resistors. This is the value worked out by much trial and error that I can stick in series with everything are all the lines that go out to the target machine to give it some modicum of protection, but without stopping everything from working. Alright, I believe that's all our capacitors and resistors. What's next? I have here 74 HCT125. There's the 5-volt buffer. That is the output buffer, this one here. Now, KiCad indicates pin 1 on components in clear but slightly obscure ways, so I like to stick a little 1 on the silk screen. Anytime I forget to do that, I usually find out because a chip goes up in smoke, so I put it backwards. So I have some more obvious cues for myself. Here is the LCX125 chip. This is very cool. This chip, its inputs and outputs are high impedance when powered off, which means it will not it doesn't have the usual protection diodes, and so you don't find yourself accidentally powering the board through its GPIOs if you use a chip like this. I forget why exactly I didn't just use a pair of these. It's probably, I suspect maybe it has 3.3 volt outputs and not 5 volt. Don't quote me on that though. I might have it backwards. Here is the big improvement in the version 3 boards. We have a MOSFET to protect against reverse polarity connection, against the power from being connected backwards. And it's time for the microcontroller. This is my favorite microcontroller. It's the Atmel AT-SAM D21E18A. It's the same microcontroller used in the Arduino Zero and a lot of the boards from Adafruit. I assume that dot is pin 1. Goes crossed. See, I made a right hash of putting that down, but it's not that precise. Looks like I still need the power regulator, the FPGA, and the LED. Oh, and a micro USB socket. Let's do the regulator. Note to self, when I do this next, I'm going to put my laptop down so I can look at it without you having to stare at the chair. Here's the 3.3 volt regulator. Turn our USB power into something we can use. There's our USB socket. finally, it's going to be the FPGA. You'll notice that there's a few not fitted components on the board. This whole right-hand side was originally a board for me to experiment with using this Atmel chip as a USB host. Also, I prefer to use Tag Connect for the programming connector for the board for the microcontroller, but I put a footprint for a standard ARM Cortex 2x5 header, which you can use with pretty much anything designed for an ARM chip. Okay, right, I see a little dot and a big dot. I think the little dot is the one I care about here. Okay, this, I need a new pair of tweezers. Oh, this is terrible. Okay, so you may or may not be able to see in the video, but this is pretty misaligned. Just going to nudge it carefully back into alignment with my tweezers. And I think it is close enough. I'd say we are done. Well, okay, now let's pull out the hot plate, which is right behind me. And hopefully that wasn't anything important. Hot plate. Okay. So, just carefully put the circuit board on the hot plate and turn it up to, I put it on the 350 setting. That's probably 350 Fahrenheit. I'm in America, so that's kind of what we get. I would be surprised if this was accurate at all. Got some heat? Yeah. Now we just sit and wait for kind of a long time. It's, oh, I forgot the LED. Let's see if I can fit the LED before it gets too hot. I can smell something melting, so hurry up here. And the LEDs keep in. Oops. There we go. All right, fingers crossed. Fingers crossed. Let's see. So the first thing that you see happening is the nice, well, ideally nice, neatly placed, neatly stenciled blobs of solder paste, which perfectly match the pads. They start melting and go all blobby and just kind of all over the place. And then you'll start seeing them just pop and turn into nice soldered joints. The first time I saw that, it was pretty magical. still just looking kind of sandy in there. I see some steam or smoke coming off it, so it can't be too much longer. This one is taking its time. Oh, and there we go. Probably barely shows in the video, but all the pads on the SWD connector have reflowed. Looks like it's the right hand side and the bottom of the circuit board that are reflowing first, so still see that? Good. Alright, now I'm seeing reflow happening everywhere. So the trick is generally make sure it works, it all reflows on one side, turn the thing around, leave it there. Starts feeling like it's getting kind of uncomfortably hot and smoky. Turn it off. Now, I can still see the solder bubbling under some of the components. That means it's not quite done. You want to stop seeing any activity like that. Okay, I'll turn the heat back on for a minute. I think I usually take them off before it's fully reflowed. When I desolder parts, I'll often see some unreflowed paste underneath. Okay, that's looking pretty good. Okay, so once everything's looking good, pick up the board, a pair of tweezers through any convenient holes, and then you're done for now. It's too hot to touch, so I have to give it a minute. Actually, I'll leave this on. I'm going to inspect it for bridges. Okay, this side of the processor looks good. I see 2 solder bridges and 2 blobs bridging 3 pins each. This side of the FPGA is just a huge mess. Oh, yeah, huge mess. That's the side of everything. Okay. This side of the FPGA, pretty messy. Oh dear. I may have actually misaligned the microcontroller enough to merit actually reflowing this thing again. That's unfortunate. First time I've done that in ages. Basically that entails just heating the whole thing up again, poking it with a pair of tweezers. until you see it actually moving. I do have a hot air reflow machine right next to me, but there we go. Just moved. Okay, looks perfect on that side now. Little messy there. Great there. Great there. Okay. That'll need a fix up with a soldering iron later, but shouldn't be too awful. Next step is doing that actual fix-up with the soldering iron. Until we've done this, it's not even worth trying hooking it up to power. Alright, let's give this a try. Cool enough to touch. So, we have a flux pin. This is a Kester 186 flux pin. Now, we can see that. Great. Put some flux on all of the nasty bits on our 0.5mm pitch part, which is most of it. All of the unhappy parts of the microcontroller, it's mostly decent, but could probably use a little touch-up. And was there anything else I wanted to mess with? No, I think that's pretty much it. Oh, sometimes the micro USB, I suspect that one here has missed a little. Alright, let's get this in here. So, step one is fill in some of the mounting holes for the micro USB socket. When I forget this, I always regret it when I rip the socket off while programming the board, attempting to program the board on the bench. This connector is a tiny bit lopsided. I would have poked it if I'd noticed during reflow, but it's too late now. Actually, I'm just going to touch them and see what happens. That might be okay. Well, multimeter needs a new battery, so I'm not going to be testing this right now. I could just eyeball it for now. Okay. So for the finer pitch components, I suspect this wouldn't happen as much if I used a footprint specifically designed for reflow, as in smaller pads. I think it's the long pads that give it more solder than it needs. Okay, that's looking great. This one's got a couple of big blobs to fix. Oops, still has a couple of big blobs to fix. Come on. Reflow? What is going on here? There's just so much solder in there that it's not getting picked up by my wick. Maybe I'm not doing it hot enough. It was on 750 degrees. Once again, probably Fahrenheit. Okay, that's a bit happier. I'm on 800 degrees. I'm using a Reflow WES 51. Soldering iron, the one that we used at university. It's not very expensive and works great. This is a pity. I was hoping to demonstrate that you could just poke it with the solder wick and have everything work out fine. Instead, get a demonstration of everything that can go wrong. And this one is needing many passes. Okay. I lost all my flux or something. This one is just as bad as the last row. Alright, yes. The lesson I always forget. Use tons of flux. Tons of flux. Now that's looking great. Fourth side, let's preemptively stick on a whole lot of flux. Now you see why I would rather use a 0.8mm BGA. I'm more comfortable soldering 0.8mm BGA than I am soldering 0.5mm QFP. I think that's kind of an unpopular opinion. BGA almost always solders just fine on the first try. QFP, well, this happens. Now, what was I going to do with this chip? I think I was just going to touch soldering iron to every pin. Whew, okay, and we're done, I think. I don't see any obvious issues, so let's try powering this up. Do I have anything with nice pins on it? That's all I have to do. Okay, so where can 5 volts go in? Come on. Ground right there. Going to poke 5 volts into it on this one. 5 volts, 0.1 amps. If all goes well, I should see an amber light. Yay, an amber light, and it's using 0.02 amps. Hooray! That means the USB side of things is not obviously wrong, obviously bad. Now let's do the target side. I think 5 volts is up here. Whoa! That was pretty bright. Okay, great. If we plug it in backwards, let's see if this works. 5 volts up top, 0 volts down there. We get the red light and 0.01 amps. Great. That's amazing. That means the protection circuitry is working fine. Great. Well, there you have it. We made a circuit board. Very superficially tested it. So, starting from that bare board and a large pile of components, a little while ago. 50 minutes ago. Okay, so this is about an hour's work so far. I haven't even programmed it and tested it yet. And it needs the test header over there soldered on. When I do 3 or 4 of them at a time, it's a little bit quicker, but yeah, here we go. Most of an hour, one reflow board. See you next time.